Section: Introduction. In this section, we discuss the importance of context in understanding actions taken by both humans and systems. Context helps us interpret the meaning of actions. For instance, scheduling a meeting during a lunch break may be acceptable under a tight deadline but not in a casual setting. Researchers have explored how context relates to privacy in computer systems and AI agents. In adversarial situations, understanding context is crucial to distinguish between harmful and harmless actions. Currently, many security systems rely on manually defined contexts or lack context altogether. Traditional security methods often use pre-written policies and access controls, which can be too rigid and fail to account for every possible situation. This can lead to overly restrictive or permissive actions and can be cumbersome to manage. Additionally, systems that depend on user confirmations can cause fatigue and grant excessive permissions. As the use of generalist AI agents grows, the need to address these limitations becomes more pressing. We observe that as the variety of contexts increases, the detail of security policies must also increase to avoid issues with permissions. Therefore, we need more research on securing systems with diverse capabilities. To tackle this, we introduce Conseca, a framework for contextual security in agents. This framework aims to ensure that every action is justified based on its context and purpose. Conseca generates timely, context-specific security policies that clarify which actions are safe and restrict others. Its deterministic enforcement protects against certain types of attacks. Conseca faces two main challenges. First, it needs to create policies tailored to specific contexts. While ideally, security experts would craft these policies, this is not feasible. Instead, we use a language model to dynamically generate security policies that align with user norms. To reduce errors, these policies include clear rationales for auditing. Second, we must ensure that policy generation is resilient to adversarial manipulation. Conseca addresses this by isolating the policy model to only consider trusted contexts, preventing outside influences from altering policies. This approach allows the model to better predict appropriate actions while maintaining security. In summary, we call for more research on scalable security mechanisms for general-purpose agent systems, present Conseca as a context-aware security framework, and share a proof-of-concept prototype integrated with a Linux agent. Section Summary. In this section, we emphasize the importance of context in understanding actions and propose Conseca, a framework for contextual security in AI agents that generates dynamic, purpose-driven security policies tailored to specific contexts. We highlight the need for scalable security mechanisms that can adapt to diverse tasks and contexts, addressing the limitations of static policies and enhancing both utility and security. Section: Background and Threat Model. In this section, we focus on agents, which are systems designed to perform a wide range of user tasks, highlighting the security challenges that arise as we scale these systems. When a user requests a task, the agent decides on the necessary actions to complete it and carries them out, often utilizing external tools. We illustrate this with the Conseca framework, which breaks down agents into two main parts: a planner, that processes user requests and suggests actions, and an executor, that performs those actions and interacts with external tools. The executor sends results back to the planner, which may propose further actions. We specifically examine agents used for computer tasks, noting their capabilities and potential for misuse. The context of a user's request includes all relevant information, such as usernames, file details, and storage locations. Agents can gather this context directly from user requests or from responses of external tools. In our threat model, we recognize that an unrestricted agent could unintentionally or maliciously perform harmful actions. For instance, an attacker might trick the agent into executing a harmful script by manipulating the context, such as through phishing emails. We assume that the agent is generally well-intentioned but may make errors. We categorize some context as trustworthy, like timestamps, while considering other context, such as third-party emails, as untrusted. The agent's objective is to take actions that meet user expectations based on the current context, which may include untrusted information. The Conseca framework serves two main purposes. It generates a security policy tailored to the user's task and context, and it provides feedback to the agent on whether proposed actions comply with this policy. To implement Conseca, developers set up hooks that trigger the policy generator with trusted context and tool documentation when a new user request is made, and they also use a policy evaluator to assess the agent's proposed actions. We describe how Conseca functions. First, a user submits a task request, which the policy generator processes along with trusted context and tool documentation to create a specific security policy. The planner then suggests the next action, which is evaluated by the policy enforcer. If the action is denied, the planner receives an explanation and can either propose a new action or seek user confirmation. If approved, the action is executed, and the results may include untrusted content. The planner then continues to determine the next action based on the task and context. We emphasize that while context is crucial for assessing action appropriateness, it can be manipulated by adversaries, potentially affecting the policy generator. We rely on developers to define what context is trustworthy, typically avoiding context controlled by third parties. While trusting more context can enhance policy accuracy, it also raises the risk of compromise. For example, an email address could carry malicious instructions, but a developer might deem addresses from a monitored domain as safe, allowing for a more precise policy. Section Summary. In this section, we focus on agents that execute user tasks by processing requests through a planner and executor, while addressing potential security threats from malicious context manipulation. We introduce the Conseca framework, which generates context-specific security policies and evaluates proposed actions to ensure they align with user expectations, balancing the need for trusted context against the risk of adversarial influence. Section: Contextual Security Policies. In this section, we discuss contextual security policies. The Conseca policy generator takes a user request along with a trusted context and produces a policy. This policy consists of a set of rules in a clear language regarding various tool APIs, along with understandable reasons for these rules. For instance, a policy for a file system tool might restrict the removal of files in a specific temporary directory, explaining that it is only for organizing temporary files. Tool APIs outline the actions that can be taken, while the policy limits these actions by preventing certain tools or specific calls from being executed. We utilize large language models, LLMs, to efficiently create these policies, as they can adapt to changes in context. In theory, any context-aware policy writer could be used to generate policies for different situations. We enhance the quality of the generated policies by using in-context learning, where we provide the LLM with a set of example policies to guide its output. Developers can also ask users to approve a policy before a task is executed, based on the constraints in their explanations. Additionally, policies can be recorded for future review by users, developers, or trusted third parties. We rely on policy experts, possibly automated, to ensure that the reasons align with the constraints. For deterministic policy enforcement, when a policy and an action are proposed, the policy enforcer checks if the action is allowed by evaluating the policy constraints. This includes checking the type of action and its arguments. When an action is approved or denied, Conseca provides the rationale for the decision to ensure transparency. In our proof of concept, we created a simple AI agent using Conseca in Python for a Linux system. This agent can access a file system tool, a file processing tool, and an email tool that can manage emails and attachments. The email tool operates within a designated mail directory in users' home directories. All tool APIs are executed as bash commands. Without Conseca, the agent follows a planning and execution process, where the planner generates a bash command and the executor runs it. This loop continues until the task is marked as complete or fails after a set number of commands. The Conseca prototype is a Python library with an API that allows us to set policies and check if commands are allowed based on those policies. A policy maps an API call to constraints, which include whether the call can be executed in the current context, a Boolean condition for the call's arguments, and a rationale for these constraints. Policy generation involves using an LLM with prompts that include API documentation, example policies, the user's task, and the trusted context. For example, if the task is to get unread work-related emails and respond to urgent ones, the policy generator would return specific constraints for sending and deleting emails. We acknowledge some limitations in our prototype, such as representing argument constraints with regular expressions. Future work may involve creating a simpler domain-specific language for constraints. Additionally, we assume that API call parameters are positional and that optional arguments are provided correctly. We can adapt to named arguments with adjustments to the policy generator's prompts. We define trusted context as the user's email categories and addresses, along with a structured view of the file system. Tool-agnostic context includes the user's username, time, and date. Section Summary. In this section, we describe the Conseca policy generator, which creates security policies based on user requests and trusted contexts, using LLMs to ensure context sensitivity and improve policy quality. We also outline the deterministic policy enforcement mechanism that evaluates proposed actions against these policies, providing transparency through rationales for decisions, and discuss the prototype implementation of Conseca as a Python library for managing tool APIs. Section: Agent Integration. In this section, we discuss agent integration. Once we set the task's policy with Conseca, the agent calls is _allowed when suggesting a new command. Conseca checks if the policy permits the API call and verifies that each argument meets its regex requirements. Commands that are allowed proceed to execution, while denied commands, along with their reasons, are sent back to the planner. The agent then includes this information in the prompt to help the planner LLM select the right action. If commands keep failing, up to 10 times, the agent reports could not complete. To add new tools to our prototype, we need to include tool documentation in the prompts for the policy generator and agent LLMs, as well as define how to extract trusted context from the tool. For instance, integrating the email tool API and part of the POSIX API took us less than a day. Next, we present case studies to showcase Conseca's effectiveness by examining our prototype's utility, how many tasks can be completed with and without Conseca policies, and its security, whether Conseca can prevent actions that don't align with the current context. We compare Conseca against 3 baselines: I, no policy; E, a static restrictive policy that blocks all changing actions; and E, a static permissive policy that allows all actions except deletions. For our setup, we conducted experiments on a Debian Linux machine connected to an external Gemini 1.5 Pro model. Before starting each task, we set up the file system with 10 users, including an admin, each having over 10 files in various folders. The mailboxes contained emails from other users about work and personal matters, some with attachments like reports and photos. We created 20 tasks that involved file system and emailing tools, all requiring subjective judgment and multiple tool calls. These tasks ranged from simple ones, like backing up important files via email, to more complex tasks, such as deduplicating files and emailing a list of the removed files. Regarding limitations, to fully assess Conseca's advantages, future work will need real data from actual agent applications instead of synthetic examples, which may not reflect the full range of contexts. With real data, we can apply concepts from red teaming and synthetic benchmarks to evaluate Conseca's benefits in real-world scenarios. In our preliminary results, we found that an agent using Conseca performs better than one with a static restrictive policy and similarly to one with a static permissive policy. The unrestricted agent completes about 70% of tasks on average. However, 4 tasks, like permission checks and organizing attachments, failed after requiring over 100 actions, while 2 tasks were too complex for our basic agent. The agent with Conseca achieves an average completion rate of 60%, as both Conseca and permissive policies deny unnecessary actions. No tasks succeed with a restrictive policy since all require right actions. To illustrate inappropriate actions, we show how Conseca's contextual security policies can limit inappropriate actions. For example, if an employee sends an email asking to forward urgent security emails, whether this action is appropriate depends on the context. The unrestricted agent might forward emails even when it's not suitable, while the agent using Conseca denies forwarding unless it's specifically for urgent tasks. Moreover, Conseca maintains higher utility than a restrictive policy. Finally, we address prompt injection attacks and defenses. Many agents using LLMs are susceptible to jailbreaking and prompt injections. Current defenses, like heuristics or anomaly detection, often overlook the appropriateness of actions based on context. Instead, Conseca builds on isolated agent models but requires minimal changes to existing designs, aiming to enhance security across all contexts. It separates policy generation from planning, providing complete context for the planner. Other research suggests incorporating a security analyzer in agent design to check if actions violate a security policy. Conseca introduces the concept of contextual policy generation that is independent of specific policy languages and can utilize existing security analyzers. Section Summary. In this section, we describe how Conseca integrates a policy checking mechanism for agent commands, ensuring that only allowed actions are executed while providing feedback on denied commands to improve future decision-making. We also present preliminary results demonstrating that Conseca enhances task completion rates compared to restrictive policies and maintains higher utility than static permissive policies, while effectively mitigating inappropriate actions based on context. Section: Context-Aware AI. In this section, we discuss context-aware AI. Similar to previous research, we utilize models that are trained to recognize behavioral norms. Other studies have applied these models to assess appropriateness and within a framework of contextual integrity. Our approach aligns with the principles of contextual integrity, but we go further by ensuring not only that data flows are contextually appropriate, but also that actions taken are suitable for the context to prevent potential harm.